Now we are going to talk about demultiplexers.
This demultiplexer is also called as a data distributor, and this is the exact opposite of the multiplexer. This demultiplexer is a combinational logic circuit which is designed to switch one common input line to one of several separate output lines. So the shortened name is DE-MUX, and this is the simple sketch for a demultiplexer. We can see there is single input line and there are several output lines, and there are switches or selectors to direct this input line to one of these output lines.
Just like the multiplexers, these demultiplexers are also classified into 4 types. These types are 1 to 2 demultiplexer, 1 to 4 demultiplexer, 1 to 8 demultiplexer, and 1 to 16 demultiplexer.
As the first example of the demultiplexers, we are going to talk about 1 to 2 demultiplexer, and let's represent it. We can draw the demultiplexer like this. This is 1 to 2 DE-MUX, and as this name suggests, there is one input. I name it as I, and the name suggests there is two outputs. I called it as Y0 and Y1. So let's find out number of selectors in this demultiplexer. It is similar to the multiplexer. We can get the number of output. In here we can get the number of output as n, and in here it is equal to 2. So if we get the number of selectors as m, we can write it m equals to log 2 to n, and it is equal to log 2 to 2. So this is equals to 1. So m will be equal to 1. So there is one selector. We can write it like this, and let's draw the table for this. Okay, there is one selector and two outputs, Y0, Y1. Okay, I consider that when the switch is, this selector is equals to 0, the I is going to the first output, which is Y0. So S is 0, the Y0 will be equal to I, and Y1 will be 0. And I consider that when the this selector is on, which is the S is equal to 1, the input is going to that output, which is Y1. So we can write it like the S is 1 and Y0 is 0 and the Y1 is I. So we can get the expression for both so we can get expressions for both Y1 and Y0. Let's find out those. In this first case, we can get the expression for Y0. Y0 is equal to, this is inversion, the S is 0, so S bar and I. And with the second case, we can get the expression for Y1. So Y1 is equals to, in here it is S and I. So these are the expression for the outputs. So we can now demonstrate this in our simulator. So now we are going to represent our 1 to 2 demultiplexer in our logic simulator, and here are the equation that we find out earlier. So let's start building the circuit. First we have one input and we can name it as I. And there is one switch. Switch means selector. We can name it as S. And also we get the inversion of the S, so we must connect a inverter to S. Like this. And we have two outputs, Y0 and Y1. So the operation between S and I is AND. So we must have two AND gates. Another AND gate. And the output of this AND gate will be Y0. So let's get an output, another output, so we can name it you can copy this name and paste it here. This is Y1. So let's connect the inputs to these gates. For the Y0, S bar is connected and the I. For the Y1, S is connected and the I is connected. So this is the logic circuit for our 1 to 2 demultiplexer. Let's check it. When the S selector is 0, as we according to the table that we discussed earlier, when the S selector is 0, the Y0 must have the output. So in here the S is 0, the I is 1, and then Y0 is 1. So when the S selector is 1, the output is Y1. So the I input is directed to Y1. So this is how the 1 to 2 demultiplexer works. As the second example for the demultiplexers, I talk about the 1 to 4 multiplexer. Let's represent it. So we can draw it like this. This is 1 to 4 DE-MUX, and there is one output. We all know that there is only one input in the demultiplexer. So I named it as I, and as this name suggests, there are 4 outputs. I named it as Y0, Y1, Y2, Y3. So let's find out the number of selectors in this demultiplexer. It is similar to the previous scenario. I take the number of outputs as n, and in here it is equals to 4, and I take the number of selectors as m. M is equal to log 2 to n. So I can write it like this. In here n is equal to 4, and now I can write 4 as 2 to the power 2. So I can rewrite it like this. So this is equals to 1. So m will be equals to 2, and there are 2 selectors, S1, S0. So let's draw the table for this demultiplexer. There are 2 switches 2 selectors, and there are 4 outputs, y1, y0, y1, y2 and y3. Okay, let's put values to this table. I consider that when the, both S1 and S0 is 0, I is going to y0. So we can write it. Both S1 and S0 are 0. So I0 is equal to I. Sorry, y0 is equal to I and others are 0. And when the S1 is 0 and S0 is 1, I consider that I is going to the y1. So the S1 is 0, S0 is 1, the y1 will be equal to I. So others are 0. And next I consider that when the S1 is 0 and S0 is 1, the I is going to y2. So S1 is 1, S0 is 0, the y2 will be equal to I. So others are 0. And as the last case, we can, when both S1 and S0 are equals to 1, I consider that I is going to the y3. So S1 is 1, S0 is 1 and I3 will be equal to I. So we can write it like this. Then we can get the expression for these 4 outputs. Let's take it. Okay. The y0. With the first case, we can get the expression for y0. So we can get, this is a 0 and this is also 0. So S1 bar and S0 bar and I. And in the second case, we can get the expression for y1. So y1 will be, here S1 is 0, so S1 bar and S0 is 1, so S0 and I. And to the y2, we can get the expression for y2 with the third case. So S1 is 1, so S1 and S0 is 0, so S0 bar and I. And for the I3, we can get the expression with the from the last case. So y3 is equal to, S1 is 1 and S0 is 1, so S1 and S0 and I. So these are the expression for 4 outputs, and we can demonstrate in our simulator. This is how we can represent 1 to 4 demultiplexer in our logic simulator, and these are the expressions that we find out before. So this is the truth table for this circuit, and let's check this circuit whether this circuit is compatible with this truth table. So this table says when the S1 and S0 both selectors are 0, the Y0 output will have the I. So first we have to give an input for the I, and the S1 and S0 is 0. So we can see the Y0 output is having the I. And as the second record, it says S1 is 0, S0 is 1. And it says that Y1 output will have the I. So let's check it. S1 is 0, S0 is 1. Yes, we can see that the Y1 output is having I input. So, as the third record, it says that S1 is 1, S0 is 0, and it says that Y2 output will have the I. So, let's check it. S1 is 1, S0 is 0, so we can see the Y2 output is having I. And as the last record, both selectors have 1, and it says that Y3 output will have the I. Let's check it. The S1 is already having 1 and we give 1 to S0. We can see that Y3 output is having the I. which means Y3 output is high. So this is how 1 to 4 demultiplexer works, and this circuit is compatible with this truth table that we find out before. In previous chapters, we talk about the introduction and some examples for demultiplexer. In here, we are going to talk about the application of them. The demultiplexer is used to connect single source to multiple destinations. The main application area of demultiplexer is communication system, where also the multiplexers are used. Most of the communication systems are bidirectional. They function both ways, transmitting and receiving signals. Hence, for the most of the application, the multiplexers and demultiplexers work in sync. These communication systems use multiplexer to carry multiple data like audio, video and any other form of data using single line for transmission. This process makes the transmission easier because it uses only single line. The demultiplexer receives the output signals of the multiplexer and converts them back to the original form of data at the receiving end. The multiplexer and demultiplexer work together to carry out the process of transmission and reception data in communication system. The next application is in computer ALU, which means arithmetic and logical unit. In an ALU circuit, the output of ALU can be stored in multiple registers or storage units with the help of demultiplexer. The output of ALU is fed as the data input to the demultiplexer, and each output of demultiplexer is connected to multiple registers which can store the data. So, the next application is the multiplexers are used as serial to parallel converter. A serial to parallel converter is used for reconstructing parallel data from incoming serial data stream. In this technique, the serial data from the incoming serial data stream is given as the data input to the demultiplexer at the regular intervals. The counter is attached to control input of the demultiplexer. This counter directs the data signal to the output of the demultiplexer where these data signals are stored. When all the data signals have been stored, the output of the demultiplexer can be retrieved and read out in parallel.